Imagine a patient walks into a neurology clinic. They've suffered a minor stroke, a tiny, localized short circuit in one specific cluster of their brain. The diagnosis is a rare condition called acalculia. By almost every measure, they are completely fine. They have a flawless memory, their grammar is exceptional, their IQ is well above average. But if you place a few objects on a table in front of them, something strange happens. They cannot instantly recognize the quantity. To know how many items are there, they have to point and count them out manually, one by one. A typical brain doesn't do this. When you look at the table, you don't count. You effortlessly and instantly perceive the threeness of the objects. We usually assume that being good at math is tied to raw intellectual horsepower. If you struggle with numbers, the assumption goes, you must be lacking in broad cognitive ability. This specific medical case proves the exact opposite. Mathematical ability doesn't emerge from being generally smart. It relies on a dedicated, isolated physical module built directly into the architecture of the human brain. Neuroscientists call this instant recognition subitizing. It is our innate biological ability to immediately identify the quantity of a small set of objects without actually counting them. And you didn't learn how to do this in a classroom. We see this exact same evolutionary trait in human infants, who can barely hold their heads up, and across various animal species. For early organisms, recognizing quantity at a glance was a survival mechanism. It allowed them to make split-second, life-saving choices, like instantly knowing which tree held more fruit, or identifying which pack of predators was larger. Because this hardware was forged by evolution, almost every human is born with the exact same foundational number sense. This biological bedrock exists completely independent of how someone might eventually perform in a math class. This innate number module lives in a fold near the top back of the head, called the intraparietal sulcus, or IPS, which raises a crucial question. If we possess this dedicated mathematical hardware, why does learning calculus or complex algebra feel so overwhelmingly difficult? The issue is that biological evolution only optimized the IPS for estimating raw physical quantities. It was never designed to decode abstract symbols. To perform higher math, the brain literally has to hack itself. It forces the IPS to borrow processing power from completely unrelated cerebral regions. First, to read an Arabic numeral, it routes visual data from the visual cortex at the back of the skull. Then, to learn multiplication tables, it recruits language centers, forcing us to rote memorize equations like vocabulary words. When an individual severely struggles with higher math, it is rarely a defect in the IPS itself. Usually, they are experiencing a transmission glitch along one of these newly forged ad hoc neural pathways. Solving complex math isn't a natural biological function. It is an improvisational feat of neural networking. And because it relies on improvised connections, it is inherently fragile and prone to failure. This anatomical reality gives us a precise understanding of developmental dyscalculia. The condition stems directly from inefficiencies in how those extended pathways connect to the IPS. Think of it like colorblindness. Dyscalculia is a highly specific, localized hardware limitation. It tells you absolutely nothing about a student's overall cognitive potential. For decades, our culture has perpetuated the myth that being bad at numbers is a sign of laziness or a failure of intelligence. We've treated a biological reality as a character flaw. Educational systems must adapt to this evidence. If the specific neural pathways connecting language to math are inherently inefficient for a student, forcing them through endless drills of brute force rote memorization is a biological dead end. Mathematics is a physical sense, rooted deeply in our evolutionary biology. By accepting that fact, we can eradicate the stigma of struggling and finally teach to the brain we actually have.